Hello student, now I am going to discuss the P block element. The last class already we finished is nothing but a S block element, nothing group 1 and group 2. Now I am going to discuss the P block element. In the P block element, what we need to know, this is a P block element we are going to discuss. In the P block element, in the plus 1 portion there is group 13 element and group 14 element. In group 13 element is there what? Boron, aluminum, gallium, indium and thallium. This is the group 13 element. Whereas group 14 element, carbon, silicon, germanium, tin, lead. And group 15 element, if you look at group 15 element, but that is there in plus 2, but here as a P block element I am writing, that is nothing but a nitrogen, phosphorus, arsenic, antimony, bismuth. And then group 16 element is nothing but a oxygen, sulfur, selenium, tellurium, polonium. And then group 17 element is nothing but a fluorine, chlorine, bromine, iodine, astatine. And group 18 element will be nothing but the neon, krypton, helium, neon, argon, krypton, xenon, rhenon and UeO. So these are the P block element entirely: group 13, group 14, group 15, group 16, group 17, group 18. The way I remember, you have to remember that way. And moreover, the difference will be there. If you look at boron to aluminum, 8 difference will be there, and aluminum to gallium, 18 difference will be there. Gallium to indium, 18 atomic number difference, here to here 32. So that way you can remember the atomic number also, 8, 18, 18, 32. This difference you will be there like that. And now if you look at these things, generally this germanium, if you look at this part if you look at this silicon and then arsenic, antimony and then silicon, selenium, tellurium, this part, and antimony, this part if you look at this part. So now, and if you look at this part, I am just putting this part. So this part and rest of this part. This part in a P block element is nothing but a non-metal, semi-metal or metallite. That means depending on the situations, they can act as a metal or they can act as a non-metal. And now this part of the P block element act as a metal, and this part of the element in a P block act as a non-metal. So this is the idea first you have to understand. That means generally you know S block element is nothing but a metal, P block element is nothing but a non-metal, but and the in between is their transition metal, but that is a wrong concept. Even in NCERT book it is written that the transition element is nothing but a present between S block and P block element, that is why it is called as a transition element, but that is not the reason. The reason is when I will go for the D block element, I will explain in detail. Just you know, there one phenomena is there, splitting of d orbital will be there, and there is a dd transition is possible from T2G to EG. Because of the dd transition, that element is called as a transition element, not because of in between S and P. And now this S P block element, there are a mixture of element is there, metal, non-metal and the semi-metal or metallite. Because of they are different in core electronic structure, that much difference is arises. Moreover, lot of exceptional case will arises in a P block element as because of different core electronic structure. So that is why here we need to study these things. Now our focus will be there group 13 and group 14 element. First we will proceed for the group 13 element. General characteristics you know very well, 5 to 7 minutes we will finish it off, and then there are certain compounds, certain structure, certain reactions we will go through. Got the point, my dear student? So let us focus for the group 13 first. In the group 13 element, if you look at, write down the electronic configurations. If I write down for the group 13 element, boron, aluminium, gallium, indium, thallium. Boron electronic configurations we can write down like this: 1s2, 2s2, 2p1. That is the number of valence electron is nothing but a highest number of n value. Corresponding orbital containing total electron is a valence electron. 1s2, 2s2, 2p1. The atomic number is 5. So helium means 1s2 is finished. So then 2s2, 2p1, this is nothing but a boron. You got the point, my dear? Now aluminium means neon code 3s2, 3p1, and then gallium means argon code 3d10, 4s2, 4p1, and then indium means krypton code 4d10, 5s2, 5p1, my dear, and then thallium means xenon code 5d10, 4f14, 6s2, 6p1. This is nothing but a thallium. You look at, my dear. Now once you will write down this way, then all the properties deviations will be very easy for you to give the explanations. Suppose I am telling about, and boron always used to show the anomalous behavior. So why? Already you know the reason. And here why it is called as a p block element. You can take any element and write down the electronic configurations. You will see the last electron will come enter to the p orbital. That is why p block element. The general valence electronic configurations for the p block element, general valence electronic configurations for the p block element will be ns2 np 1 to 6. This is the general valence electronic configuration for the p block element. ns2 np 1 minus 6, because p orbital capacity maximum is 6. So this will be general valence electronic configuration for the p block element. You got the point, my dear student? So now you look at the properties. We will go through very effortlessly. Size. The size order down the group, generally we know, as the number of cell will increase, the distance from the nucleus to the valence electron will be more. So that is why the size will increase. That is what we know. But in this case, what will happen, you look at boron, actual order will be what? Boron, aluminium, gallium, indium, thallium. These will be the order according to our logic. As the number of cell will increase, then the size will increase. So that is why, but here this is not the actual order. There one exception will be there. The gallium has a lower size than the aluminium, has the indium and thallium. These will be the actual order. Why this order will be observed? Reason, you look at the gallium electronic configuration 3d10. D orbital has a shielding effect. It has a very poor shielding effect. D and F orbital. What is shielding effect? Suppose you look at, there is a nucleus. If the inside electron is there in a s orbital, it has a very, and this is a valence electron. This electron is there in s orbital. S orbital can shield the nucleus properly. That means it can cover the nucleus properly. That is why the attraction of this valence electron to the nucleus will be less force of attraction. Less force of attractions will be there. But whereas whenever the inside electron will be there, the d orbital, so then the d orbital not able to cover, electron is there in a d orbital, because of its diffuse nature and the big size, the d orbital cannot cover the nucleus properly. It has a poor shielding. Poor shielding means not able to cover the nucleus properly. So poor shielding effect, then the valence electron will be exposed to the nucleus and the nucleus will attract the valence electron more powerful way. That is why there will be a contraction of size. That is why the gallium has a lower size than the aluminium, because of poor shielding effect of the d orbital. That means the d orbital not able to cover the nucleus properly and the valence electron will be exposed to the nucleus. Whereas when the electron will be there in a s orbital, it can cover the nucleus properly. That is why the valence electron will not be exposed to the nucleus. That is why the size will be bigger, where the d inside d orbital electron will be there, size will be smaller. D and F orbital, same poor shielding effect will be there. And now because of that, the gallium, this exception is appearing in front of your eyes. And regarding the ionization energy, ionization energy order will be nothing but a boron. Down the group size will increase, ionization energy will decrease. As because of size increase, force of attractions of nucleus to the valence electron will be less. You can easily knock out the electron. But here the order will be like this: boron, thallium, then indium, then gallium, then aluminium. This is a order is observed in case of a ionization energy. Why? Because the reason is, you can explain from here. In case of a thallium, D and F orbital has a poor shielding effect. Because of that, the nucleus will be more powerful, which is attract the valence electron towards itself. To remove that one, you need more amount of energy. That is why this difference is arises. And 4D is more diffused compared to 3D. That is why indium is greater than gallium. Same logic by way you can explain the phenomena, my dear student. Got the point? And now this is about ionization energy. Then what about the electronegativity? If you look at the electronegativity order, then what will happen, my dear? Electronegativity order observe boron, after that thallium, and then if you look at that things, thallium, after that the indium, and then gallium and aluminium, almost the same order will be followed. Same type of order will be followed. The region is same region, whatever I explained. As because of poor shielding of D and F orbital, so then the nucleus will be more powerful to attract the electron. That is why this order will be followed. So this is nothing but ionization energy, size, electronegativity, all those we explain. And then in case of a melting point and boiling point, very random order will be followed. There is no consequence. Only one thing you have to remember: the gallium melting point is nothing but a 30 degree centigrade. So that means at summer, gallium will be in which form? Liquid form. These informations you need to remember. Otherwise there is no random order will be observed in case of a melting point and boiling point. Only you have to remember the gallium melting point is 30 degree centigrade. At summer, gallium will be which form? In very liquid form. You have to understand these things. And depending on the metallic bonding, like sodium, potassium, S block element, they are, because of their bigger size, so their metallic bonding is weak. But when we will go for the aluminium, gallium, indium, because of their size is not a big like sodium or potassium, that is why their metallic bonding will be strong. They will be comparably, they will be hard compared to sodium and potassium. This way you have to understand the logic. Now when you understand these things, then we will go for the explanations of their certain compounds. Certain compounds, they are oxide, all those things we are going to explain, and certain compound what will form, all those things we are going to explain. Like boron, they used to form their oxide B2O3. Like aluminium, Al2O3, and then gallium, Ge2O3, indium, In2O3. But the thallium has a most of the time is used to put like this. That means thallium oxidation state is nothing but a what? +1 oxidation state. Other used to show +3 oxidation state. Moreover, this oxide is acidic in nature. This Al2O3, Ge2O3 amphoteric in nature, and this will be nothing but you have to understand. And down the group, the oxide basicity will increase, like that scenario. And now, if you look at over here, the thallium used to form like a alum type compound, like K2SO4, you know, that is thallium SO4, Al2SO4 whole thrice, 24H2O. Like that, potassium alum, thallium used to form this type of salt. They will ask you, the thallium plus 3 is a good oxidizing agent. Good oxidizing agent. Good oxidizing agent. Oxidizing agent. Explain this phenomena. Explain this phenomena. Thallium plus 3 is a good oxidizing agent. Explain this phenomena. How you will explain these things? Because the thallium, the stable oxidation state is +1 instead of +3. Why? Because Already we write down the thallium electronic configurations will be nothing but the xenon code 5D10, 4F14, 6S2 and 6P1. You look at in case of a thallium, what will happen because of the poor shielding of D and F orbital, poor shielding of F and D orbital electron, the nucleus will be more powerful to attract the valence electron. So highest value of N is 6, corresponding orbital S and P containing total electron 3. Out of this total electron, this 6s2 electron will not participate in bonding, not participate in bonding. So that is why, because of the poor shielding, 6s is more closer to the nucleus, which will be experience more force of attractions by the nucleus. So that is why 6s2 will not participate in bonding. Rather than the +3 oxidation state, it will show what? +1 oxidation state, and this phenomena is called as a inert paired effect. This phenomena is called as a inert paired effect, and because of this inert paired effect, instead of +3 oxidation state, the thallium plus stable oxidation state will be +1. So that is why everybody wants to attain the stability. Immediately it will accept the 2 electron and it will be converted to thallium +1. That means it will snatch the electron from other species. That means it will oxidize the other species. That is why thallium +3 is a good oxidizing agent. Moreover, as it forming the +1 oxidation state like a potassium or sodium, that is why it used to form the like a potassium type a compound. The same reason in terms of the poor shielding we explain this inert paired effect, and later on you will see zirconium has the same size of a hafnium. Because of this inert paired effect, the lanthanide contractions will be there. What reason I told for the inert paired effect, because of poor shielding, same poor shielding will be utilized to explain there is a, because of the poor shielding, the force of attractions will be they are more in valence shell electron, there will be contraction of size, that is called as a lanthanide contraction, and because of the lanthanide contractions, that zirconium has almost same size of hafnium, 4D element almost have a same size of 5D element. This is the basic thing you need to understand over there. Now once you understand these things, then you will go for the next things. What do we need to know? That certain compound and their things what is happening over there. Suppose if you look at very important compound, that boric acid, already I discussed during the N factor, boric acid is a non-protonic acid. It can accept 1 unit of OH minus, that is why it's nothing but N factor is 1. This boric acid, when you will treat it with sodium carbonate, then borax will be formed, Na2B4O7, and then Na2B4O7 water of crystallizations will be there, 10H2O. In this compound is nothing but we used to present like this. Actually it will be present like this, that you look at this boron, this is nothing but a boron, oxygen, and then boron, oxygen, it will be presented like this. Structure of borax, boron, oxygen, boron, boron, oxygen, boron, boron, oxygen, boron, boron, oxygen, boron. And now here OH, and then here OH, and then here OH, and then here OH, and in middle boron, oxygen, boron. And then overall there will be Na, 2 Na plus will be there, 2 Na plus, and then here there will be 8H2O. This is the structure of borax. Because why you need to remember the structure of borax? Here they will ask how many boron atom is there, sp2 hybridized. This boron 3 sigma bond is means sp2. This is also this boron sp2. Whereas this boron atom 4 sigma bond sp3. This boron atom 4 sigma bond sp3. They will ask you in the borax structure how many sp2 boron is there, how many sp3 boron is there, how many bond is there, boron oxygen boron bond is there, bridging bond. Like that question you need to, they need to ask. And moreover, the overall charge of the salt is +2. N factor for this one will be nothing but how much, my dear? The total charge on the cation or anion, if you take the mod value is a N factor, so N factor will be equals to 2, whereas N factor for H3BO3 is 1. So these are the way they will put forward a questions. You got the point, my dear student? It's clear to everyone? Again, the two things also you can study from the books. On heating of H3BO3, what are the product is possible? On heating of Na2B4O7, what is the Borak-Biss test? Na2B4O7 on heating, it will be produced that sodium metaborate NaBO2 plus B2O3, that is the glassy bead formations will be there. That glassy bead will test with copper oxide, cobalt oxide will produce the blue color, that is called as a Borak-Biss test. Moreover, on heating of H3BO3, what are the different product formations will be there? You can go through simply. That is a things you need to know over here. Now, another very important things you need to know over here, that compound like AlCl3 and then B2H6. If you look at this B2H6, how they are forming this B2H6. So, B2H6 if you look at, this B2H6 is nothing but a sodium borohydride. There are several methods is there, but I am showing you one reactions. Even with lithium aluminum hydride, with the BF2 reactions, same productions will be there, they will form the B2H6 as a main product. This is called as a diborane. This is called as a diborane. And this diborane structure specifically like this. Actually BH3 structure will be like this, and then this is a BH3 structure. You know this boron has a vacant p orbital, hybridization is sp2, electron deficient. Another BH3 will be like that, and where they are as a vacant these things. Now this sigma bond will be donated over here, and this sigma bond will be donated like this, and then they will form this type of compound, where they will form like this type of compound like this. I think here you can check this bond will be around 97 or 95, this bond will be 120, and this bond length will be around 130 picometer, this is 122, this is 121 picometer, and this will be 134 picometer, this is bond length. And now this bond is nothing but a 2 electron which is sharing between boron, hydrogen and boron. That is called as a, that is why this structure, this is called as a 2 center 3 electron bond, a 3 center in between hydrogen, boron and hydrogen, 3 center 2 electron bond, or it is called as a banana bond, or it is called as a banana bond. This is a electron deficient substance. Inside bond angle is 97, outside bond angle is 120, inside this outside bond length is 121, inside bond length is 134 picometer. So these are the things you need to know. The same way, aluminum chloride also will be dimerized. You know the aluminum chloride structure. Here aluminum has a vacant orbital, another aluminum this chlorine, and this is has a vacant structure. So they also will be dimerized like this, and then they will form Al2Cl6, because the aluminum has a vacant orbital. They will form like this type of compound. This is another very important compound you need to know over here itself. This is nothing but Al2Cl6. This is nothing but Al2Cl6. This is nothing but Al2Cl6. Very important compound. And whatever I told you can go through. Borax on heating, what will be given? Borak-Biss test I told. H3BO3 on heating, what it will give. So these are the reaction you need to know. Another very important, the last point on these chapters I want to mention. So that is nothing but the reactions. The reactions of B2H6 with ammonia. What will happen? That reaction. That is a very important reactions. Moreover, the ammonia can be make a coordinate covalent compound with BF3. Suppose BF3 is there. So this lone pair can be donated over here. So then they will make a coordinate covalent bond like this. The ammonia already has 3 hydrogen like this, and this is making the vacant orbital of boron is there, and in that vacant orbital of boron it is making the coordination. So this is forming like this. This is the coordinate covalent bond formations will be there. And moreover, if you look at this B2H6, how they will form that compound, the reaction with ammonia. This B2H6, if you look at this B2H6, 3 things you need to know regarding that one. B2H6, this B2H6 is nothing but a reactions with ammonia. Reactions with ammonia, if you look at, what will happen, you know, the reaction with ammonia, first of all you have to understand it will form this type of compound, that NH3 NH3 which will be coordinated to BH2 and another NH3 which will be coordinated to this one, and this overall charge will be nothing but a plus, and here there will be BH4 minus. This type of ionic solid formations will be there. This is a BH, this way this will be formed like this type of ionic solid type compound will be formed. Whereas B2H6 NH3 excess and then high temperature, then that time it will be formed boron nitride, inorganic graphite formations will be there. Inorganic graphite formations will be there. And now this B2H6 NH3 excess and then high temperatures 1:2 ratio, then you will get the inorganic benzene B3N3H6, inorganic benzene or borazine formations will be there. Inorganic benzene or borazine formations will be there. Borazine formations will be there. These are the some highlighted reactions I explain. Then the last point, very interesting, they will give you BF3, BCl3 and BBr3. Which one will be strong Lewis acid? Like that questions they will give you. And BCl3 or BF3 will be covalent in nature, like the barium fluoride I explained. You can explain via Pajan's rule, or you can explain by the ionization energy is very high. That way you can explain. Now you look at, if they gave you the which will be Lewis acidity order. To explain that things, what you need to know, boron, fluorine and fluorine. What logic I am telling you, boron has a vacant orbital and fluorine has a lone pair of electron. Now boron orbital also 2p, fluorine orbital also 2p. So then it can be back bonding, it can possible, which is called as a 2p back bonding. Whereas in case of a boron chlorine, dear, you look at, here boron has a 2p and chlorine electron is there in 3p. So here 2p and 3p back bonding. But you know 2p and 3p compatible of size will not be there. In case of a bromine, 2p, 4p back bonding will be there. So that is why maximum extent of bonding will be there with boron and fluorine. So that means fluorine already will donate to the vacant orbital of boron. So that is why the boron was initially very hungry, but already it will get the electron from the fluorine because of the matching of the 2p matching. Back bonding will be maximum. So that is why in BF3, boron will not that much interested to take the electron from the outside. That is why Lewis acidity will be what? Least, because according to the Lewis acidity, the substance which can easily accept the electron from the outside is nothing but a Lewis acid. As because of the size compatibility, the extent of back bonding will be maximum in BF3 because of 2p back bonding will be there. That is why it will be least Lewis acidic in nature, whereas in 2p, 4p in boron and bromine is the very weakest back bonding. That is why boron still will be hungry. So that is why it can take the electron from the outside very easily. That is why Lewis acidity will be maximum. So that is why the Lewis acidity order will be BBr3 is greater than BCl3 is greater than BF3. So that is what the things you have to understand. I hope, my dear student, you understand the thing. And now I am finishing this P block element, the group 13, and the next class I am going to discuss is the group 14 element. Thank you very much. Thank you all.